It's difficult for a non-English speaker to follow the two previous ones, and particularly when talking in part about the same problem as Malone did. So what I have to do first is to acknowledge also participation for the last part of my talk of John Mitrofanis from Sydney, who's part of significant participation to what I'm going to show you, which is in addition to what was the breakthrough about last year. So what I want to say is by going to electrons to photons is to go from electrical stimulation to irradiation with the light, and particularly laser light. It's not optogenetics, but it's metabolic interaction photomodulation. So when we think about it, we do have a brain, and it is shy. It is hidden in the skull. It has a function, but also it may dysfunction, and then it creates symptoms which most of the time are due to a disease. And we doctors, we have to treat the symptoms and, if possible, the disease. What about Parkinson's disease? What is the problem? We know it's due to degeneration of cells, dopaminergic cells in substantia nigra, as you can see it, which produce normally dopamine, which is, in my opinion, the most important, at least in our field, neurotransmitter. And when you have a destruction of this structure and the loss of cells, then, of course, dopamine is strongly reduced, which leads to a triad of Parkinsonian symptoms, which are made essentially of tremor, which is the most visible and impressive, but not necessarily the most disabling, and bradykinesia and rigidity, which are really the source of the difficulties of those patients. Parkinson's disease is not a lethal disease, but the symptoms are extremely disabling. So we have to do something, and we have therapeutic options, which part of them have been said already by Malone, and this will help me to go quicker. Medication is replacement therapy. If you give to the patient a precursor such as levodopa, which crosses the brain barrier, reaching the brain, it is decarboxylated and leads to dopamine. And it has been said already today that it is a miracle drug with a wonderful improvement of all the symptoms of the triad. The problem is that after 5 to 7 years of continuous use and increasing doses of this medication, we see the appearance of side effects and dyskinesias, levodopa-induced dyskinesias, which are most of the time more disabling than the disease itself. The alternative was, and still maybe is, neurosurgery involving the destruction of targets, the thalamus, the pallidum, many others. STN is not a real good target because it has more risk than others. And the effect was also restricted not to the whole triad, but quite often mostly to the tremor. And we had also complications, quite quick complication occurring during the surgery, particularly as you can see it here, when the lesion is not where it should be at the tip of the green target, but a little bit far away. Just to inform you, I was not the surgeon who operated this patient. So is there anything else we can propose to the patient to have the benefits without having too much of the inconvenience? And the breakthrough discovery that I had the chance to leave was in 25 years ago, at least, during a thalamotomy, where I was trying to make clear the position where we should make the lesion. In other words, not to make sure that we are not in the wrong situation. Then we do that by different means, but also by electrical stimulation to check what is the activity of the place we are in. And we had the privilege to observe that playing with the frequency and not using the classical 30 hertz frequency stimulation, that closing to high, what we call high frequency, 100 hertz, then we saw the reverse of what is taught at school, which I taught to many of my students, that excitation lead is a consequence of electrical stimulation. But at those frequencies, that's the reverse we observe. It mimics lesion in terms of making the structure not working, like if it were destroyed. And this is interesting because it is adaptable, and also it is reversible, and it's always good when you know that your surgeon can be reversed. So we thought at that time that deep brain stimulation at high frequency might be the solution. And you can see that during surgery, you check where you are, and you check actually the existence of the effect. When I ask my assistant to stop the stimulation, you see the tremor recurs. Stimulation on, the tremor disappears. Stimulation off, in a few seconds, it will again start again. So what are the very few examples? I won't go through all the indications we have now, but in Parkinson, for instance, I can show you that 3 targets may be efficient. If you stick an electrode into the thalamus and turn on the stimulation, in this young patient with mixed tremor and strongly disabled by these movements of particularly for writing, my colleague Pierre Pollack gives him a magnet. He will turn on the stimulation, and you will see that within 2 periods of tremor, the tremor disappears, and the patient is available for doing all the clinical tests the neurologists like to do. And if we stick the electrode in another target, which is the pallidum, then we might help the patient who have dyskinesias, levodopa-induced dyskinesias, that you can see here. They are described as Balinese dancers. That's the best we can find to describe that. That's finally more disabling than the tremor itself quite often. And Pierre is turning on the left stimulator, and you see that within seconds, the dyskinesias disappear bilaterally, but only transiently on the ipsilateral side, meaning that we have to operate the patient bilaterally. Then if we go to the target subthalamic nucleus, for which Malin Delong has been extremely instrumental, showing all the benefits and the interest in the circuits of motor control, then we can have a beautiful result in a patient having severe advanced symptoms. You see this patient before surgery is tiptoeing because of the off-period dystonia. He is not able to stand alone. If you could see him from close, then you will see poorly looking because he cannot shave, cannot brush his teeth. And this is the same patient 3 months later without any medication, bilaterally stimulated into the STN, which, by the way, is very well tolerated. He does the clinical signs. He will stand up alone. He will walk. And it was a few weeks before the Vienna Movement Disorder meeting, so he gave us a tour of valse. So you can see that those electrodes are placed in different targets. We may also show what happens in the PPN for gait disturbance. And they are stimulated at 130 hertz, which is the best usually used frequency. Then we move to other indication. I'm just showing very typically what happens to dystonia. This little boy had a deficient, mutated DYT1 gene, and he had appearance in his childhood of this uncontrollable movement disorder of the leg with distortion, with a fixed modification of the ankle, for instance. And 2 months later, after being stimulated bilaterally into the GPI, the pallidum, you see that he's biking normally. He is currently a young lawyer in Brussels, and he was invited by the Breakthrough Foundation last year, and he gave me the award, so it was a very emotional moment. We can see also that if we go to another target, which is the subthalamic nucleus, you've heard of it, in the same type of indication. This is a young lady in Shanghai operated by my colleague Bomin Soon. She is also strongly improved. So another example where the same disease or some symptoms are improved by different targets. So it has led us to consider a new vision of the brain, and I would say that several targets may improve one disease. One target may improve particularly in several diseases, including obsessive-compulsive disorder, which apparently has nothing to do with abnormal movement. And then what is important also is when you record on them, Manon said that there is typical patterns for each disease, but what I want to say is that all those abnormal patterns belong to a same type of disturbance, and in all those targets for, I would say, all the diseases we tried, for instance, in STN, if you record for PD or for dystonia, for OCD, and dystonia for OCD, you get something which is made essentially of bursting and higher rate than the normal, which may help to have a provocative vision of how the brain functions, where the normal functioning is widely distributed and with a random type activity, which is a little bit what Corey said somewhere this morning, if I understood correctly what you said. And when the brain does not function correctly, it has finally one way, not too many, has one way to go wrong, which is to go into this bursty and higher rate type of pattern. Then if we look at what I've shown is that we have symptomatic effects and they are reversible, which is good. But when you stop it, what you see is that the disease has still progressed, continued to progress, nothing has been changed. So there is no neuroprotective, no curative aspect of DBS, and we have now a quarter of a century of experience to make sure that we are not wrong about that. So neuroprotection is really the holy grail, and can we achieve a new therapeutic breakthrough by finding something else? And this is where our cooperation with the Sydney group was useful, because some of the people in John's lab were interested in healing of cells as a general phenomenon. And there is a lot of literature, not necessarily in the best journal, showing that irradiation with near-infrared photomodulation within the range of 600 to 1,000 nanometers had a metabolic effect, which the mechanism seems to be known. It activates photoacceptors such as cytochrome C oxidase, improves mitochondrial function, and increases ATP synthesis, and finally lead to some of healing of those suffering cells. Then we tested that in mice, and you see that the interest of near-infrared is also that it penetrates a few millimeters into the brain through the tissues, not the rest of the spectrum. And then you can, with the mouse, irradiate its brain. So we took MPTP mice. You see the normal mice, just injected of saline, they explore their open field, and then the MPTP ones, you know, they are kinetic, they don't move too much. And if you give them MPTP plus infrared irradiation, you see that they move, not as well as the saline controls, but much, much better than the MPTP. And at the autopsy, when we count the cells into the substantia nigra, we see that in the red square, the left column shows the cell loss, and the right one shows that the number of cells is quite equivalent to the normal one. So there is a neuroprotection, behaviorally and histologically speaking. Then we went in direction of human application and wanted to have a preclinical program. We designed a system to be implanted in monkeys, and it is made of a laser source, no, this way, of a laser source which is connected to a fiber going into the brain through a catheter, and here just powered by a battery, which is finally nothing but the battery of a DBS stimulator. And then the electrodes are implanted on the midline because so we are at equidistance of the substantia nigra at the level of their coordinates. And when we activate the system, we have a diffusion of light which irradiate both sides at the same time. Then what does it do? You can judge by yourself. We have here a clinical score, the higher the worse. So the red curve corresponding to MPTP monkeys shows that their behavior is strongly impaired, while the green curve corresponding to the monkeys which have received the MPTP but also have been irradiated the way I showed you, they are almost normal. And if we go to the autopsy, that's the same. We have, in terms of counting cells, as comparing the NER treated with the MPTP pure for TH staining in blue and Nissl in red, and also the terminals in striatum. You see that there is definitely a neuroprotection, and this has been published, and the paper just appeared in Annals of Neurology. You can look at it, and Fanny Darlot is the postdoc who was in charge of part of this program. Now we are engaging, and that's my almost last slide, to the clinical trial, which is the objective of all that, and it's scheduled for 2016. You see here the last prototype of the implant which will be used. Similarly to what I showed you in monkeys, we are going to implant through the ventricle, which is a procedure that we use already exactly for cluster headaches, for instance, or other indication. It's rather safe. It's like a ventricular puncture, and the tip of it is placed at the height of the substantia nigra, and we can shine light this way. We expect to prove that the concept of neuroprotection is okay. About curative effect, meaning that even if we stop things, did we stop really the disease, or did we compensate the cell loss for a time? We'll see next year. And this is a team. The stars correspond among the Clinatec, and Clinatec is the institution that the CEA has built for us for translational medicine. That this is where next year we will start that, and you are kindly invited to join us at that time. Thank you for your attention.
We have time for several questions.
Continuous stimulate. I mean, how long do you have to really stimulate with the light therapy? Is there a? Do you know what the minimum requirements are?
Well, that is something we have to make more precise during the clinical trial. What we have seen already with the different type of preclinical experiment in mice, in rats, in monkeys, is that we need a very low amount of irradiation. For instance, the mice have 90-second irradiation 2 times a day and every day. Same about for the monkeys. We have looked at continuous irradiation. Obviously, we have less benefit. So are we in a bell-shaped curve, or is that something else which happens? Obviously, there is a large margin for us to adapt because the patterns of irradiation which are used now are far below the 2 things. One, the energy which is available in the batteries, so it's not a problem on this side. And also we have kept all the phenomena under the limits of regulation. We don't have the right to go over 2 degrees Celsius. And we have an MRI method to measure precisely. We did that in the rats and in the monkeys, that we keep the irradiation not delivering more than, not too much heat, not to overpass the limits. Actually, we stay below 1 degree. So it seems that there is, of course, adjustment to be expected, maybe for the best, and this is currently one of the work in progress. While we are going towards clinical trial with these parameters, we have started a new basic research to precise these aspects.
Hi, Melissa Miller. I was just wondering, so you're using MPTP as your PD model in your model organisms. There are lots of different mouse models for PD. I was wondering if you had any success with the genetic models rather than the chemical model of PD.
So that's an extremely good question. Someone has done it in some manner. That's a group from EPFL in Zurich working with Hilal Lachouel, who is now in Qatar. And they have made a series of animals with surgical transfection with mutated synuclein, alpha-synuclein. And they have obtained symptoms, and they have cured it by external irradiation. We are doing an experiment with using engrailed mice, which have been given to us by Alain Prochiance at the Collège de France. And actually, it's not really a PD or alpha-synuclein, it's an aging model. And so far, we are at 9 months, almost 10 months. The two groups, irradiated and not irradiated, obviously age the same way on different criteria, including the treadmill system. So we are looking, and I am ready to buy, at reasonable cost, any kind of truly alpha-synuclein model in mice. That's one of the goals for the moment, of course, because the more we have. What we did is, beside MPTP, we didn't show the results. We use the Ertel and Sawyer model of CISO-HDA striatal injection, which induces a unilateral degenerescence of the nigra, which we used for something else before. And this is also improved. That's a thesis which will be defended in January by one of Florian Renard, a student of us. So in this case, there is a benefit. So MPTP and CISO-HDA models are responding to that. Engrailed, which are not truly close to movement disorders, do not show, so they will be used as a negative control. And what we have seen, and it has been published in recently, the one from EPFL and Hilal Lachouel, I don't remember where. PLOS One, 1 or 2 months ago. This is also a benefit, but it's not a spontaneous model. So the odds are good so far. One thing I forgot to mention is the DBS is designed for, at least is used for advanced stages of Parkinson, which makes, by the way, easier to check the benefits. Here we are in the totally different situation because we want to protect. We know that at the time of first symptoms appear, 60 to 70% of neurons have been already destroyed. So we have to, we are in emergency to save the remnant, and which causes a problem for the clinical trial because the patient will be poorly symptomatic, post-symptomatic. I don't know exactly how early we will take them. It depends mostly on their acceptance to be part of the clinical trial. But those patients will have very tiny symptoms, difficult to analyze, with a high variability also, meaning that we will have to follow them quite long and see if the two groups are different. And we will use for them also another additional non-clinical criterion, which is the levodopa intake with the PET scan, of course. This might be the most difficult part of the study. Are we or not improving the patient before they show it too late?
Okay, thank you very much.